Welcome to the 30th lecture on computational mathematics with Sage Math. In this lecture, we will explore solving system of linear equations. So, let us start with an example. So, suppose you have a system of linear equations. These are three equations in three variables x1, x2, x3. So, we have seen how to solve such a system of linear equations using solve command. So, let us just recall that and solve this system using inbuilt function solve. So, how do we do that? First, we need to declare x1, x2, x3 as variables. So, var x1 underscore x2 x underscore 2 and so on, and then we use solve function solve, write the set of equations in inside square bracket separated by comma, and then we want to solve with respect to variable x1, x2, x3. So, let us run this. So, when we run this, it will give me a solution of this system. It takes little bit time to begin with, and later on it will become faster, right. So, the solution is x1 is equal to 1, x2 is equal to 1, sorry, x1 is equal to minus 1, x2 is equal to 1, and x3 is equal to 2. If you want to get this solution in terms of dictionary, you can say solution underscore dictionary is equal to true. This is solving system using inbuilt function solve. However, you can also write this equation as a matrix equation. So, you can write the coefficient matrix A, which will be a 3 by 3 matrix whose first row is 2, 3, minus 4, second row is minus 1, 2, minus 1, third row will be 1, 2, 3, and then the B is the column matrix minus 7, 1, 7. So, let us see how we are going to declare. So, we declare this matrix A, which is the coefficient matrix, and the matrix B, this we will declare as a vector, because by default when you declare a vector, it is thought of as a column matrix. So, therefore, we have A coefficient matrix and B is the right hand side. Now, we can solve again using this solve function, but slightly different. So, there is a function called solve underscore right, and in the bracket you write B. So, A dot solve underscore right. See, there is also notion of solve underscore left, because sometimes you write Ax instead of Ax equal to B. If you write X transpose A is equal to B, then in that case you can use solve underscore left, but mostly commonly we use solve underscore right. That means we write the set of equations as Ax equal to B. Okay. So, let us run this. When we run this, we should this I did not execute. So, let me execute this again. When we execute A dot solve underscore right, it will give you solution as a vector. Now, suppose if I want to store this in S is equal to solution, and then we can check whether this is a solution. So, if it is a solution, I should get A star B, this should be equal to A star S, this should be equal to B, and that is what you can see here. So, you can check whether this is double equal to B, right. The answer is true. So, there are two ways of solving system of linear equations in Sage Math. One, you can use solve command, and other one you can use solve underscore right. In that case, you have to think of this system as a system declared as Ax equal to B, right. Now, let us play with this matrix, because the solution at present we are using this inbuilt function, and we do not know how this solution is obtained using this inbuilt function. So, let us look at some concepts that leads to solving this system of linear equations using what is called Gaussian elimination methods. Next, let us look at how to extract rows and columns of a matrix by matrix multiplication. So, we have already seen that Sage provides a function called A dot columns, which will extract columns as a vectors. Similarly, A dot rows will extract rows of A. But when you want to perform matrix multiplication and various other operations, it is very it is convenient to think of the rows and column wise. So, let us see what what we can do. So suppose you have a matrix, random matrix A, 4 cross 4 random matrix, which is matrix of integers whose entries varies between -10 and 20. So in that case, let us see how do we extract first column, second column, third column without using Say's inbuilt function, just as a matrix multiplication. So what we can do is, let us write 4 cross 4 identity matrix. Let us declare that as I4. This is can be obtained using identity underscore matrix, and in the bracket you write the order of that matrix, and then E is equal to I4 dot columns. So we are extracting E as column vectors. So first column vector is generally we write as E1, which is 1 0 0 0, second E2, which is 0 1 0 0, and so on. So in general, EI is ith unit vector along the coordinate xi, right. Now let us see what happens. Suppose we multiply A by E by first column of the identity matrix, namely 1 0 0, right. So what will you get? So if you say, for example, j is equal to 0 and look at Ej, that means E0, that is the first column of A, and when you multiply by A, what will you get is the first column of A. That is what you can see here, -9 4 -1 1. Similarly, if I take j is equal to 1, this will give me the second column. If I take j is equal to 3, it will give me fourth column, and that is what you can show. You can see. So you can obtain ith column of a matrix A by A times EI, right. So that's a vector obtained by multiplying A with EI on the right hand side. That is what it means. So ith column of a matrix can be thought of as A times EI. Similarly, instead of multiplying on the right hand side, suppose we multiply on the left hand side. Suppose we multiply EI by A, right. So what will you get? So if I multiply by EI on the left of A, and what you get, you can see here, this is the first row of this matrix. So E0 times A is first row. If I take I equal to 1, and then it will give me second row. If I take I equal to 2, it will give me third row, and so on. So we can write any row and any column by multiplying EI with A on the left or on the right. Okay, when you multiply on the left, it will give you rows. When you multiply on the right, it will give you columns. So that is one way of thinking of rows and columns of a matrix. This actually so basically we are visualizing as vectors, right. Okay. In case you multiply, let us say, EI with A and with EJ, what will you get? A times EJ is a vector, column vector, and then you are multiplying by EI. So what you are getting is, this will give you actually dot product. So it will be ijth entry. So for example, in this case, when I is equal to 2, j is equal to 1, what will you get is what you are going to get is third row, second column element, which is 5, and you can verify that third row and second column, third row and second column entry is 5. This is what you got. So ijth entry you can also obtain using this. Now suppose you multiply, look at EI and multiply by EJ. Okay, so EI you think of as a column matrix, and then multiply as EJ as a row matrix. So EI times EJ transpose, this will give you again a 4 cross 4 matrix, whose in this case I plus 1th row and j plus 1th column will be 1, remaining all will be 0. So in this case, this is I equal to 2, that is why you can say the third row, and j is equal to 1, so that is second column, third row and second column entry is 1, remaining all are 0. So that is how you can obtain EI times EJ, right. So this actually helps us to understand matrix multiplication and many other things. Now, when you want to solve system of linear equations, generally you must have seen that in order to solve this, we generally do some kind of operations, row operations. So, there are 3 row operations which leaves the solution unchanged. What are they? You can interchange any 2 rows, is same as saying interchange any 2 equations. When you interchange any 2 linear equations, the solution does not change. You can multiply any equation by a scalar, that again the solution does not change, or you can add any 2 rows. You can add one row to another row, and or you can take any combination of all these things. So, these are called elementary row operations, because when you apply these operations on set of linear equations, the solution does not change, and this can be translated to row operations to the system of linear equations Ax equal to b. So, and I am sure you must have solve many problems by using elementary row operation, and the idea behind using elementary row operation is that you want to convert the system into a simpler system. Of course, I mean, you can ask what is meaning of a simple system. So, for example, if the coefficient matrix is identity matrix, all you are looking at, if the coefficient matrix A is identity matrix and you are have a system of linear equation Ax equal to b, that is same as saying x1 is equal to b1, x2 equal to b2, and so on, xn is equal to bn. So, that is the easiest system you can think of, right. So, if some way if you can convert the coefficient matrix A into identity matrix by system of elementary row operation, that is the best thing you can ask for. So, that is the basic idea. Even if you have upper triangular matrix or lower triangular matrix as a coefficient matrix, then also solving system of linear equations becomes much simpler. For example, if you have upper triangular matrix, then you can solve the system by what is called back substitution. If you have lower triangular matrix, you can solve this by forward substitutions. So, that is the basic idea of converting this matrix into matrix which is simpler to deal with, right. So, let us look at what are the elementary row operations that we have. So, suppose you have a matrix A which is 1, 2, 3, 4 up to 16. So, 4 cross 4 matrix, and this is another way of declaring a matrix. So, we have declared the elements of this matrix as a list, and then we are declaring the order 4 cross 4, right. And then let us store this A into B. So, copy of A into B, right. So, let us do that. So, B is this 1, 2, 3, 4, 5, 6, 7 up to 16, 4 cross 4 matrix. Now, suppose we want to do some elementary row operation. So, if I, for example, there is one elementary row operation called swap rows. Swap rows I j will swap ith row and jth row. Okay. So, if I run this A dot swap rows 1 comma 2, what are we expecting? We are expecting third row and second row to be interchanged. Okay. So, let us run this, and when you call, what happens to B? So, you can see here the second row was starting with 5, now that has become third row, and the third row was starting with 9, that has become second row. Now, you can ask for what has happened to the matrix A. So, if I let me insert a cell here, and if I ask what happened to the matrix A, the matrix A has not been changed, it remains as it is, only B has changed. Whereas, if you had declared B equal to A, then whatever operations that you are going to perform on B will also be reflected on A. So, A will also change. That is the reason why we are taking copy of A rather than declaring A equal to B, right. Okay. Let us look at other elementary row operations. So, for example, if I look at B dot rescale and then underscore row 1 comma 10 means the second row will be multiplied by 10. Let us look at, we want to multiply the third row by 10 and then see what happens. So, third row was starting with 5 was 5, 6, 7, 8, and it has been multiplied by 10. Again, you can check that A would not have changed, A will remain as the original matrix. So, this is the scaling any row. Now, suppose you want to for example, multiply a row by some scalar and add to another row. For that you can use b dot add multiple of underscore row 1 comma 2 comma 10 means what? The the second row in this case will get multiplied by 10 and will get added to here 2 means third row will be multiplied by 10 and it will get added to the second row. Now let me interchange here, let me say here 2 and this is 1 and then let us ask for what happens to B. So what has happened to B? You can see here now this first the second row that is multiplied by 10. So this is 90 plus 50 140 and then 10 into 10 is 100 plus 60 160 and so on. So this this b dot add underscore multiple underscore of underscore matrix row I comma j means what? This comma let us say s, this then what will happen? It will multiply this s row, s plus 1th row in this case by j plus 1th row by s and add to r plus 1th row. That is what it is doing. So these are the elementary row operations that already are inbuilt and you can perform them, right. Okay. So and you can keep on applying these operations. Now when you apply these operations, as I said, when the idea of applying these operations in terms of finding solution is to convert this system into simpler form so that solving becomes easy. Of course, in case of 3 cross 3 matrix, 4 cross 4 matrix, it is not very difficult, but if you are dealing with let us say 1000 linear equations in 1000 many variables, then solving will be an uphill task. In that case, if you can convert the matrix A into simpler form, it would become much simpler. So in that sense, and when you apply any row operation, let us say we applied row operation to A and obtained a matrix B, then A and B are called row equivalent matrices. Row equivalent matrices means what? The solution will not change. The A and B, if Ax equal to B, if I look at Ax equal to let us say B and another matrix M which is row equivalent to A, Mx plus Mx equal to B, then this Ax these two systems are actually equivalent. They represent actually the same system of linear equations, right. So there is a matrix called Echelon matrix to a given the Echelon matrix is actually a matrix. It is a in which in case there are some 0 rows that will appear at the bottom and non-zero rows will be at the beginning, and also if you look at in any row, if I take any 2 rows, let us say I row and jth row, if there is a non-zero element in ith row and non-zero element in jth row, then what should happen if in case j is bigger than I, then the non-zero element on the ith row should be to the left of non-zero element to the jth row, or okay, and any element after, if you look at in any row, if there is a non-zero element, then in that particular column all the element following that should be 0, and that element generally we call as a leading element. So leading element, if it is non-zero leading element, if you look at that particular column, all the entries after that will be 0. That these are called Echelon matrices. And if you are given a matrix A, which is let us say this is the matrix A, now you can convert this matrix into an Echelon matrix using inbuilt function which is called Echelon form, A dot Echelon form of the matrix A. So it will, what it will do, it will apply elementary row operations and it will convert into equivalent matrix which is an Echelon matrix. So let us apply this. So when we apply this and look at what has happened to A, of course A remains as it is when you apply to this Echelon matrix. Let me call this as A1 and let us see what is A1 now. So A remains as it is, and if I say what happened to A1, then A1 is actually Echelon matrix which is a row equivalent to the matrix A. A and A1 are row equivalent. You can also write another thing, you can call A dot echelonize. So, what it will do, when we saw that when we say A dot echelon form, A does not change, right, whereas if I say A dot echelonize, A itself will change. So, let me say what is A in this case. So, A itself has changed. So, you can see here why this is echelon matrix is that there are 2 0 rows which are appearing at the bottom. Here first 2 rows are non-zero, and then leading entry in the first row is 1, and here also 1, and this entry is to the left of this non-zero entry. That is why it is called echelon matrix. Okay, you can if you have bigger example, you can take some arbitrary matrix, try to convert into echelon form. You will understand much better. Of course, this echelon form of a matrix need not be unique, but what is unique is actually called RREF, reduced row echelon form. So, you keep on reducing this till you cannot proceed any further, right. So, for example, it's possible that I can make these elements also 0 if it is possible, I don't know. So, in that case we try to keep on applying this elementary row operation till the point from which you cannot reduce any further. Okay. So, this is in case, for example, if A is an invertible matrix, RREF of that will be actually identity matrix. So, let us see what is RREF. In this case, RREF is same as the echelon form of A. So, that in this case both are the same, so it hardly matters, but however, in many cases it may be different. And RREF, that means reduced row echelon form of a matrix, is unique. That is one advantage of applying RREF, right. Now, suppose if you want to write your own function to convert any matrix into RREF, then it is quite simple. So, this particular code gives you step by step conversion of a given matrix to RREF. So, all these steps like converting the matrix, interchanging the rows, and scaling a row, adding any the scalar multiple of row to another row, etc. You can perform, and then you can run this. So, let me just show you this code. Let me just run this code and then see here. You can see here it is performing step by step. So, let us look at what it is doing. So, this was the original matrix, and what it is doing, it is converting this into 0 first, that means the second entry, then this into 0, and then it will go to the next step and next step. Once this is making this 0, and then next step will make this particular entry 0, and things like that. So, you can keep on continuing this till you get identity matrix. In this case, since the matrix is invertible, row echelon form of this matrix, reduced row echelon form of this matrix will be identity matrix. And so, this row echelon form or reduced row echelon form is very useful. This you can use it for solving system of linear equations, and many other computation in linear algebra actually boils down to elementary row operation. So, this we will keep coming, we will keep using this RREF in several concepts, especially when we want to do certain computations. So, let us look at how we can solve this system of linear equations using RREF. So, this I am sure you must have already done it, but let me demonstrate this using Sage Math. So, how do we do that? So, let us take a system of linear equations Ax equal to b. In this case, these are 3 equations in 3 variables, and what do? We convert, we make an augmented matrix. So, we augment this vector b to this matrix A. So, there is an inbuilt function to find augmented matrix. So, you simply say A dot augment, and in the bracket you write B. So, for example, let me just run with only this. When you do that, you can see here this column B is augmented to the matrix A. But you can also mention, so many times when you do this augmented matrix, generally you put also a vertical bar just to differentiate between the coefficient matrix and the last column which is inserted. So, that option also is there in Sage. You can say what is called, let me just say here this, yeah, let me say this is called subdivide is equal to true. So, when you say subdivide equal to true, now you can see there is a vertical bar that is put in order to distinguish the matrix A and this vector B. Right. Now, once you have created this augmented matrix, then what you can do, you can apply RREF to this augmented matrix, row reduced echelon form to this augmented matrix, and whatever you get on the last column will actually reflect the solution. So, let us say in this case, when we do RREF to this augmented matrix, last column is 1, 2, 3. So, what this equation represents, the Ax equal to B has been converted into this x1 is equal to 1, x2 is equal to 2 and x3 is equal to 3. So, that means 1 to 3 is a solution of this system of linear equation, right. So, that is, and now you can extract the last column using sub matrix or using just the indices, right. Now, suppose you have another set of system of linear equations Ax equal to B, and in this case suppose we apply RREF to augmented matrix. In this case, what are we getting? We are getting here, you can see here what we are getting, the last row in A has become all 0, whereas this side is 1. So, this last row will represent 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 1. So, that cannot happen. Therefore, this means that this system of linear equations does not have a solution. So, when you apply RREF to augmented matrix, and if you see that on the right hand side, if there is something non-zero, on the left hand side, that is the row corresponding to the matrix A, if it is 0, that reflects that this system does not have a solution. However, in case let us say last row has become all 0, let us take an example. So, suppose we take this system of linear equations. So, A is 1 1 2, B is 2 4 minus 3, C is the first row is 1 1 2, second row is 2 4 minus 3, third row is 3 5 minus 1 and so on. And now, if I apply RREF to this system of linear equations, then what we get? We get last row is completely 0. That means, what does it imply? It implies that this last row is x1 times 0 plus x2 times 0 plus x3 times 0 is equal to 0, which is vacuously true, which is always true. But this actually has only 2 equations in 3 variables. So, for last equation, what does it represent? x2 times x2 plus minus 7 by 2 times x3 is equal to minus 17 by 2. So, and then the first equation is x1 plus 11 by 2 times x3 is equal to 35 by 2. So, this system actually there are 2 equations in 3 variables, it will have infinitely many solutions. So, in such situation you have infinitely many solutions, and there are many other things that can be explained using this notion of row reduced echelon form. So, for example, you can find inverse of a matrix, you can find rank of a matrix. Rank of a matrix will be nothing but non-zero rows in row echelon form, right. So, so for example, if you look at this matrix A, and when we applied RREF to this matrix, then what we got was this matrix whose first 2 rows are non-zero, remaining are all zeros. Therefore, the rank of this matrix will be 2. So, let us look at another use of RREF in finding inverse of a matrix. So, suppose you want to find inverse of a matrix, let us say A is this matrix. How do we find its inverse? What we can do is we can augment the identity matrix to A we augmented one column. Rather than one column, you can augment even a matrix of appropriate size and then apply RREF to this. So, A dot augment identity matrix 3 by 3 and then subdivide equal to true and then apply RREF. So, that is what you get, and what you have got here actually this last 3 rows and 3 columns is the inverse. So, let us extract that matrix, in A1. So, what are we going to extract? We will extract this last 3 rows and 3 columns. So, how do I do that? We can use sub matrix, and this is starting from 0th column, that is the first column, 0th row, first row, and take all the columns, right, and this take from 0th row, take and third column, that is the 4th column, take all of them. So, this is your A1, and now you can check whether A times A1, A times A1 is it identity matrix. The answer is true. Therefore, this is the inverse of the matrix A. So, actually this is nothing but, when we find the inverse, it is nothing but solving system of linear equations. So, actually what we are doing, we are solving A times some first column of B, which is equal to identity. So, that is why you augmented here identity, first column of identity matrix, here augmented second column of identity matrix, and so on, right. So, that is actually it is solving this 3 system of linear equations in 3 variables and whose coefficient matrix A is common, right. So, this is one way of finding inverse. Of course, Sage has inbuilt function to find inverse of a matrix. You can for example look at A dot inverse and then see whether you are getting the same thing. This should be equal to the same thing A1. Let us print this A1 and this A dot inverse, they are the same thing. So, what we got using RREF is same as inverse of a matrix using inbuilt function, right. Next, let us look at just another way of visualizing or looking at this solution or system of linear equations. So, what we have, suppose we have this system of linear equations, 3 equations in 3 variable. This set of linear equations you can also write as A times x1, x2, x3 is equal to B. So, if I look at this, I can write the same equations as x1 times the first column of A plus x2 times second column of B plus x3 times third column of A. So, this is first column of A, this is second column of A, this is third column of A. So, x1 times first column of A plus x2 times second column of A plus x3 times third column of A is nothing but B. So, what it means is that B is linear combination of columns of A. That is what exactly it means. So, in case let us say alpha 1, alpha 2, alpha 3 is a solution of this system, then alpha 1 times first column plus alpha 2 times second column plus alpha 3 times third column should be equal to B. Okay. So, that is another way of visualizing this system of linear equations. So, let us just verify this quickly. So, how do we verify this? It is quite simple. So, let us first declare A and B for this system Ax equal to B, and then what we will do, we will find solution of this. So, let us find a solution using inbuilt function A dot solve underscore right. So, that is the solution, and once you have the solution, let us see what is the solution in this case. S is the solution, which is a vector, and now what we will do, we will look at the first entry of S multiply by first column of A plus second entry of S multiply by second column of A and third entry of S multiply by third column of A. That should give me B, which is 24 minus 11 minus 20. So, let us verify that. How do we do that? So, we will write simple, first we will extract columns of A. How do I extract columns of A? So, columns of A we can extract as A dot columns, and that I am putting it in small a. So, these are the 3 columns of A. Now, let us look at, we can write a simple code. So, for ith entry of S multiplied by ith column of A, right, and this do it for all these I. So, for I in range, in this case 3, range 3. So, this will give me list of S1 times A first column plus S2 times second comma S2 times second column plus S3 times third column, and then sum all of this. So, sum this, take the sum, and this would give me B. That is correct. This is the B, 24 minus 11 minus 21. So, that is a very convenient way of actually visualizing solution, and many things, especially in the concepts in vector, in vector space, will be very easy to kind of or very convenient to look at in this form. Okay. So, let me leave you with few exercises. These are again simple exercises to explore this RREF. So, look at this system of linear equations, solve this using RREF, and look at this system of linear equations, check how many solutions does it have. And the last one is you must have also solved system of linear equations using Cramer's rule. So, try to see how we can solve this system of linear equations using Cramer's rule. So, in case of this, you need to learn how to replace a particular column of A by this vector B. That is only thing which is needed in this case, but that I am sure you should be able to figure it out. Okay. So, thank you very much. We will see you in the next class.